Hi dear colleagues, we're starting the lecture 10. Our current title, Automorpic Correction of Jacobi Form. This construction works very well in the case of Jacobi forms in one variable, the case of Eichler-Zagier Jacobi forms, but also we can use it for Jacobi forms in many variables. But let me start with the following theorem. You can find it in the third paragraph of the Eichler-Zagier book on Jacobi forms. The formulation of this theorem is the following. Let phi be a weak Jacobi form of weight k and index m. So we consider the situation described in the book of Eichler-Zagier. Then we can consider its Taylor expansion in Z for Z equal to 0. And all Taylor coefficients f and tau are quasi-modular form. Of weight n plus k. I give you today the different proof of this fact. Our method, I call this method automorphic correction, works very well. In this case, it gives a different proof of this result of Eichler-Zagier. Moreover, we can generalize this method without any problems to the case of Jacobi forms in many variables. And in the case of many variables, this result is the form, our form of automorphic correction, gives very nice and very constructive result, which is ever better than this formulation in the case of Jacobi forms in one variable. So, but first of all, I would like to discuss quasi-modular forms. What is it? And our first subsection today will be modular differential operators. We start with the differential operator in tau with this normalization 1 over 2 pi I. We use this normalization because we can rewrite this differential operator in terms of our formal variable q. So q is as usual 2 to the power 2 pi I tau. And this operator acts on any holomorphic or meromorphic function in the following way. We have to multiply all Fourier coefficients by its index n. So this is why I use this normalization. So this natural differential operator transforms holomorphic form into holomorphic form, but this operator is not modular in general. So it means then, if I denote this by d, then d does not keep the property to be modular. But in one special case, this is still true. Let's consider the action of this operator on Jacobi, on modular function of weight 0. So we can consider weak modular form. Weak, it means that we accept poles at infinity. Means that Fourier expansion of this function has the following form. The index n in greater or equal to minus n, where n is a natural number. So this function has a pole of order capital N at infinity. And now I would like to analyze the modular behavior of the action of the differential operator on f. Maybe I can use another slide. F is a modular function. It means that this function is invariant with respect to all elements in the full modular group. Now we can apply the operator d to the left and to the right hand side of this equality. On the left hand side we get c tau plus d to the power minus 2 d f0 a tau plus b over c tau plus d is equal to d f0 tau. So the differential operator d transforms weak modular functions with poles at infinity, into the space of weak modular form of weight 2 with respect to the full modular group. So for the weight 0, the operator, the differential operator d, is a modular operator. What can we do? For the classical modular form of weight k, I would like to consider the following operator. So we fix a modular form of weight k. Then we can define the following operator. We divide the modular form f by the Dedekind eta function to the power 2k. Then we apply the differential operator d, and then we multiply the result by the same power of the Dedekind theta function. I would like to analyze this operator and to calculate what function do we have. The elementary calculation shows that it's equal to df times eta to the power 2k minus f 2k eta to the power 2k minus 1 d eta, and we have to divide by the power, not 2, by the power 4k, the square of the denominator. The result is the following. I have df to minus 2k. Then we have the logarithmic derivative of the Dedekind theta function times the modular form f. So this is our operator dk. What type of modular transformation do we have for this function? The Dedekind theta function is modular with respect to the full modular group. Therefore, this function is a modular form of weight 2 weak modular form, maybe with some pole at infinity, with respect to the full modular group SL to Z, but with a character. The character will be the multiplier system of the Dedekind theta function to the power minus 2k. This is the second factor, but we have to multiply this function to the first factor. So we see that this product, in fact, belongs to the space of maybe weak modular form of weight 2 plus k with trivial character. To have a better formula for this function, I have to analyze the logarithmic derivative of the Dedekind theta function. And this is our next task. So I would like to calculate the logarithmic derivative of the Dedekind theta function, where the Dedekind theta function is given by the following infinite product. We have used this product several times in our course. Our problem now is to calculate the logarithmic derivative of the Dedekind is the Dedekind, maybe I write down better its modular property. This is a modular form of weight 1/2 with respect to full modular group Z, SL2Z, with a multiplier system by V eta is a root of order 24 from 1.